We expect that there might be some way to make this more efficient, and here's where you get into the unfortunate issue of people's names getting attached. It's not like you can go, oh, what kind of shape do I get? Oh, it's a trapezoid. Here, you kind of have to know what you're looking for, but we can easily find it. Let's do a tab here. What we're looking for is Heun's method. And our best friend, Wikipedia, is going to come up at the top. That's nice. OK. Just even the blurb here sounds promising. Hey, may refer to the improved Euler's method. What are we using now? Euler's method. What would I like to do? I'd like to improve it. So yeah, let's do this. In Heun's method, we're going to see something very, very similar in structure. All right. So here's just a nomenclature thing. For whatever reason, calculus analytic people decided to pick h as their a small step instead of delta t or delta x. I think they didn't want to lock people into x or t's. I find it more confusing, but just know as long as you see an h in these things, you're talking a delta t, a small step. And you'll notice what we've got here is the same thing, initial value and differential equation. What's new is this part here. So this is the formula we want to grab. So we're going to grab that, we're going to copy it, and we're going to put it in our notes here because it's so handy. There we go. So that's going to be our formula. Notice it has the same end thing. My next y is my old y plus, and you notice the formula here, hey, it's a half times two other things. So it's the average of two things. Hey, what was trapezoid rule? It was the average of two f values. Has the same roots. It's a little more complicated because there are t's and y's running around. So I'll just show you the graphical interpretation of this. Very similar in nature, but what it does is literally take Euler's method and say, yeah, that was a good start, but it lacked something. We've got our initial value, and we find the slope with Euler's, find a slope. This slope here is equal to f of t naught y naught. I'll call it ti yi here, because it's the general case. We're going to go for delta t, and we're going to get a new point. This point here would be Euler's method prediction. Euler's prediction. But we know that that's not great, right? Euler's prediction has some error in it. So one of the things we can do is say, all right, so I picked a slope at the beginning, but it's not the only slope. In fact, I know the slope should change as we move along here. That's the problem. So what we can do is also find a new slope here. I know the solution's close to where I want to be. So let's find the slope here. So we're going to take the slope at Euler's prediction. And that is just f of ti plus 1, and what they're calling y tilde here, y tilde I. It's like an intermediate guess. This point here is ti plus 1, y tilde. And then what they say is, oh, well, that's great. I had a slope. I followed it. It gets me roughly in the right ballpark. But there's another slope I could get there. Hey, what would be a good, if I had to pick one slope, not the beginning one, not the last one, how could I combine them in a nice way? Take the average slope and follow that. So if you look at the formula that we had a page back here, I'm going to find where Euler's method gets me. That's the y, they use I plus 1, sorry. And then I'm going to find the slope at the beginning, the slope where Euler's method would have gotten me, and I'm going to do a half of that times delta t. So I just take the average of the slopes. So it looks incredibly complicated at first, but all it's doing is following straight lines and saying, hey, I have two slopes. Probably the truth is somewhere in between them. Let's take the average of those two slopes. Fortunately, it's super easy to write that up because it's almost identical to Euler's method. So we're going to take our Euler's method as a template. We'll save it one more time, and then we'll save it as ODE Heun. And we'll change the name. All right. The inputs are identical. Everything's identical except the updating function. So everything else is perfect. It's just when we get down to the bottom, what we want to do here is say y tilde. I'll use the same kind of phrasing. Y tilde is actually equal to this. There we go. Let me just go back to the notes for 1 second to confirm that. Right, y tilde is the old y plus h, delta t in our world, times f. Y tilde is y, the old y, plus the f of yi times delta t. And then the real new y is this over 2, delta t over 2 times f of the first slope, which is this guy, plus, we're dividing by 2, so it will be an average, but right now we're just adding these two things. T of I plus 1 and y tilde is the y value we use. Y tilde, close bracket, semicolon. There we go. So we are just copying out the formula from the slide here. Delta t over 2, f of ti plus 1, y tilde, that's the most important part there. Otherwise, we're not transforming anything at all. And let's see how this works. So what we're going to do is the same thing we did with our integrators. We're going to solve things a couple of different ways. And let's call it let's call this t Euler and y Euler. Let's call this t Heun and y Heun. Everything about the input is identical. It's a solver. They both do the same job. They both take the same kind of inputs. And just for the sake of illustration, I'll plot that thing there. The only thing I need to fix down here is this is y Euler. So we'll tweak that in a second. Let's just try running it and make sure it works. Ah, lovely. I think we still have like 800 points, so that's not really a fair comparison. Let's go back down to 100 points. There we go. So this is Heun's method. Notice there's no visible gap when we take a first glance at it. When we zoom in sufficiently, we can see there's a tiny bit of deviation between the two solutions, but not much. Way lower than Euler's method because it's using a more sophisticated, not a lot more sophisticated, mind you, but a little more sophisticated slope estimates. It uses two of them and averages them instead of just using one at the beginning. And so what we can do here is beef up our error summation, error summaries, and say Euler's method error and Heun's method error. And we just need to say what these things are. All right, so I'm going to simplify this a little bit now. We've got the analytic end. Let's call it Euler's error is y Euler end minus the analytical. So again, depending on what variables you define for these things, you can do it different ways. Heun error, sorry, is the Heun's method endpoint minus the analytic. And then we just fill in the print statement to match. Euler end and Heun error. I think that should do it. Everything that changed should be on this screen right here. All right, let's give it a try and just make sure it runs at all. I guess we can't really see the output, so let's see the output. There we go. All right, clear the screen. And run this guy here. Lovely, okay. Just out of curiosity, if you had to guess, how much would the error go down by, do you think, for Heun's method as we double the work? By what factor? 4, 1/4, yeah. That's a pretty good guess, because that's what trapezoid rule did. And what we should see is something very much along those lines. In fact, that's exactly what we see, yeah. So we'll get rid of the graph here. So Heun's method goes down by a factor of 4 every time. Notice 5 to 20, 20 to 80, 80 to 360. And for the same amount of work, you already have higher error here, and it only goes down by a factor of 2 every time you run with Euler's method. So it behooves us to not use the completely naive. I mean, Euler's a great place if you were trying to invent calculus. That's where you would start. But if you're trying to solve things numerically knowing calculus, something like Heun's method, which is just a little more refined but has a huge payback in terms of accuracy, that's the kind of thing you would want to use instead. So in terms of efficiency, there's no question that Heun's method is far more efficient. For the same amount of work, we have to do twice as much work on each interval, but the payoff is way more than a factor of 2 in terms of reduction of the error.